We have a probability distribution as shown for different values of x. K is a constant. We're asked to show that k equals 12 over 25. So if we take each of these, k over 1, k over 2, k over 3, and k over 4, those are the different probabilities. They must add to give 1. Because we have to have one of the values because it's 0 otherwise. Now you can either add these fractions together, 1 plus a half plus a third plus a quarter, but best to just put it all in your calculator, which gives 25 over 12. K is equal to 1, and therefore k is 12 over 25 as required. We're asked to show in a table the values of x and their probabilities. This is often a good idea anyway, but we've been asked specifically to do it. So x and the probability that capital X equals x, got 1, 2, 3, and 4. So now we just need to take our k and divide by each of these as we go along. So 12 over 25. If we divide by 2, we get 6 over 25. We divide the original by 3, 4 over 25. If you divide it by 4, 3 over 25. You can even add these up, 18, 22, 25. So it all checks out. All right, here's where it gets interesting. The value of 3 independent observations of x are denoted x1, x2, x3. Find the probability that the first observation is greater than the second plus the third observation. So let's systematically work through how this could happen. Well, the first one could be 4. That's the highest possible value. And then we could be followed by a 1 and a 1. We'll worry about the probability of that in a minute. We could have 4 and then 2 and then 1. Or we could actually reverse it and have 4 and then 1 and 2. Now, if we increase x2 or x3 anymore from these later two, then it's going to end up equaling 4 or being greater than it. So actually that is the only way we can do it when the x1 is equal to 4. And then if we go down to 3, the only way it can happen is if we have 1 and 1 as our answer. So that's the only way it can possibly happen. So let's work out each of these probabilities. We've got them from the table. So the first one's going to be 3 over 25 times, remember we times them. It's like we're going along a tree diagram. We're going 4, then 1, then 1, times them together. So 3 over 25 times 12 over 25 times 12 over 25. We can just square this one. Okay, we'll work out that in a minute. For this next one, it's going to be 3 over 25 times 6 over 25 times 12 over 25. And then for the one after, you just reverse these. So actually you can bring them together and just double it. And then for the 3, we've got 4 over 25 times 12 over 25 squared. All right, just got to carefully input that into your calculator now. Just check it every now and then because I nearly made a mistake there. So that's the first one. Is it worth writing it down? I don't think so. I'm just going to keep going. Of course, you can use the fraction button as well. It's often just a bit easier to use division. It's still doing the same thing. Okay, so that's the first 3. And remember, I'm adding because it's or. There we go. So 288 over 3125. It doesn't mean an awful lot, so I quite like, even though that is an exact answer, to just write it as a decimal as well. We could round it to 3 significant figures, or maybe we just leave it exact in this case. 0.09216. Nice. Finally, in a game, a player notes the values of successive independent observations of x and keeps a running total. The aim of the game is to reach a total of exactly 7. Determine the probability that a total of exactly 7 is first reached on the 5th observation. So let's sort of play the game and see what happens. Now, if we started with 2 and then got a 4 and then a 2, we're already above 7. So we're going to need to be scoring low values to get to 7 on the 5th attempt. So let's start by just getting the lowest values that we can. 1, 1, 1, and then on the final one, we'd get 3. Okay, so if we have 4 ones in there, we'd have to get a 3 in there as well. Now, what we can think about is how to rearrange this. And maybe I'll do that now before I consider any other ways of getting 7 on the 5th attempt. So it could be that 3 goes first, and then actually the last one will be 1, or 3 could go second, or third, or fourth. So there's actually 5 ways that we can arrange 5 things where 4 of them are the same. In fact, this comes from it's 5 factorial ways of arranging 5 things, but we could, as we swap the ones around, we could swap them around in 4 factorial ways, and we'd still get the same arrangement for a given placement of 3. And then you could even divide by 1 factorial for the 3, but that gives 5. And sometimes we write this as 5C4 or 5C1 as well. So I'm just kind of trying to link into the ideas of arrangements. You don't actually need that knowledge here. You can just do what I did and write them all down. But this would speed things up if you can spot it. And I'm going to talk a little bit about something else. So the word banana, how many different ways to arrange all the letters? Well, there are 6 letters that we're arranging. So 6 factorial ways to arrange 6 things. But all the A's could, for each configuration, the A's could be swapped around in 3 factorial ways and the N's in 2 factorial ways. So this is taking it a step further from when you only have 2 objects, but it's the same kind of idea. I'm going to work out the probability of this now, I think. So to get 4 ones, it would be 12 over 25 to the power of 4. And then I need to times by the probability of getting a 3, which from above was 4 over 25. But remember, there's 5 different ways that can happen. So that is our probability. I'm just going to bring it down. Okay, there goes here. Right, now, is there any other way that we could get this total of 7? Well, what if I introduced a 2 into the proceedings? 1, 1, 1, and then a 2, and then we'd have to have another 2. So we can also arrange our objects in this way. In fact, we've now got 5 objects, so 5 factorial. 3 of them are the same, and then another 2 of them are the same. This, I can't remember if I already mentioned this, but this is essentially the fundamental idea behind the binomial distribution and even the binomial theorem when you're expanding brackets. We're looking at how these 2 things can be arranged, and we end up with 5C3 in this case. You can put this in your calculator, or you can do it without. It's going to be 5 times 4 times 3 factorial over 3 factorial, 2 factorial. So the 3 factorials cancel, the 2 factorial is just 2, so we're going to get 10. Actually 10 ways to arrange this. It's going to take a bit of time to do it by hand, but you could do it by hand. If you're not confident with the factorial stuff, you can do it. So if we, all you got to do is work systematically. Keep one of the 2's at the very end, and then just move the other one. It would be quite easy to make a mistake, to be fair. Okay, so that's all the ways when there's a 2 at the very end. And then let me fix a 2 to the 4th one, but there's not allowed to be one at the end one. Okay, that's all the ways. Now I'm going to fix a 2 here, but there's not allowed to be 1 here or here. I'm up to 9, so the last one is going to be if I fix a 2 second, I'm not allowed to have 1 here, here, or here because I've already dealt with them. And that's our 10, okay? Don't really want to be doing that, to be fair, but you could. And so finally, for the probability, it's going to be 10 times 12 over 25 to the power of 3, and then I'm timesing by 6 over 25 squared. Oh, okay. Right, we're ready just to stick both of those in our calculator and add them together. Okay, it's pretty epic. Nearly there. Right, we get 0.10616, which I will, and extra bits, and then I'll round that to 0.106. Right, that's the hardest bit, probably of the paper, and it requires you to really be on it with your arrangements. I hope that makes sense. C kind of built us up to it a little bit. D took it to the next level. I've talked a lot about the factorial ideas. Do read up on it a bit further if you're not happy. Well done. Thanks for watching.